Good morning, everyone. I'm going to present experiment number 4, matrix addition using ununified memory in CUDA. This experiment is part of a CUDA parallel computing coursework for the year 2025-26. We will look at how ununified memory simplifies GPU programming. The goal of the experiment is to perform matrix addition on the CPU using CUDA ununified memory model, especially the CUDA Malloc managed API. We want to understand how ununified memory eliminates the need to manually copy data between the CPU and GPU. We also compare two versions of the program, Ununiform 1 and Uniform 2, and use the NVProf tool to measure and analyze execution line on both CPU and GPU. What is CUDA ununified memory? Before we look at code, we have to explain ununified memory. In traditional CUDA programming, you allocate separate buffer for the CPU and GPU, then call CUDA memcpy to transfer data between them. Ununified memory removes the complexity with CUDA malloc managed. A single pointer is valid on both CPU and GPU. The CUDA runtime and automatically migrates data pages between host and devices wherever they are accessed. This simplifies the code significantly, though it does introduce some overheat due to the page falls on the first axis. Environment setup. For this experiment, we used Google Colab with the Tesla T4 GPU. The CUDA toolkit is pre-installed on Colab, and we use the NCCB4 Jupyter plugin to run CUDA C++ file directly from a notebook. The workflow is first installed, and then write the CUDA source code using write file magic and command, compiles it with NVCC, and finally profile the binary using NVProof. We ran two binary ununified 1 and uniform 2. The CUDA kernel. This is the art of the program. The sum matrix GPU kernel, it decorates with double underscore global double underscore, which means it runs on the GPU. Each thread computes a unique 2D position using thread IDX and block IDX. Then the 2D row column coordinates are then flattened into a 1D index using the formula IDX equal to IY into NX plus IX. We include a boundary check to make sure we don't go out of bounds. Each thread then adds the corresponding elements of the matrix A and B and stores the result in matrix C with 102 into 102 block of 32 into 32 threads each. We have over 16 million threads running in parallel, one per matrix element. Memory allocation and parallel launch. Here, how the main function setup and runs the experiment. We define a 4096 into 4086 matrix that roughly 67 million elements per matrix. All four arrays A, B, host ref, and GPU ref are allocated using CUDA malloc managed. We configure a 2D grid of 128 into 128 blocks, each with 32 into 32 threads. Before timing the actual kernel, we run up a warm-up launch that triggers the initial page, migrates from host to host. Then we launch the real kernel called CUDA device synchronize to wait for the completion and measure the elapsed time. At the end, CUDA free is used to releases all four arrays. And here NVProof result, uniform 1 CU file. Like, look at the profiling result for Uniform 1. The first version, the GPU kernel itself completed in just 0.008487. seconds, while the CPU took only 0.053 seconds. For the same operation, it took like the seconds. That's there is a speed up above like 60 times. However, notice that API called breakdown that CUDA launches kernel consumes 87 milliseconds, and the CUDA set device took 191 milliseconds only. The ununified profiler shows 769 CPU page faults and 192 KB of data transfer from host to host. These immigrates pages from one axis. Then this is the NVProof result uniform input. The second version uniform intro shows similar kernel perform 0.08 seconds. The CPU sums here took 0.89 seconds, giving up the same order of speedup. Notice the difference in the API breakdown. There is no large CDA launch kernel time here because the kernel dispatch overhead is much lower. The CPU page default dropped from 769 to 577, and the host to device transfer reduced from 182 KB to 128 KB. This tells us Uniform M2 causes less memory. Then memory migration. The device to device transfer stayed the same at 64 KB in both cases. Let's compare both. Um, the GPU kernel time is nearly identical, like 836 milliseconds and 835 milliseconds. So the core computation is same. The key difference is that API overhead and migration. Uniform M1 had a 87 milliseconds kernel launch overhead and 769 CPU pages false, while Uniform M2 had almost no launch overhead and only 577 pages fault. The host to device transfer were 196 KB only, and our Uniform M2 is 128 KB. Second version uses memory more efficiently. Both add a GPU page fault groups. The takeaway is actual parallel computing is equally fast. Conclusion takeaway. To summarize this takeaway from this experiment is uniform memory significantly simplifies UDA code. PUDA malloc managed removes the need for memory managed seconds. The second is GPU is dramatically faster. Kernel ran in under 1 millisecond compared to 18 millisecond on the CPU, which roughly 100 times faster. Third, unified memory is not completely free. Page defaults and page migrates to go at over it, which can observe clearly in the NV proof output. Fourth is the warm-up kernel launch is important. It pure migrates pages so that time Rhino does not include programming patterns widely used in HPC. Thank you.